students, welcome back to our course Environmental Modeling and Simulation. In today's class, we will continue our discussion on Gaussian Plume Model that we finally derived in the previous lecture, and we are going to look at certain situations where our assumptions made in the previous lectures when we were deriving the Gaussian Plume Model are no longer relevant. And the first assumption I want to start with is when the height of the chimney is not 0, when it has an effective height h. So, in the previous class, when we integrated our model, we integrated so that cu dy dz, the integration limit for y were minus infinity to infinity, which makes sense. The integration limit for dz were 0 to infinity, which is relevant when there is no chimney, when the burning or the combustion or the release of the pollutant is happening on the ground level. But what if it is not happening at the ground level? What if we have a chimney and then the effective height is h and the emission is happening at this height h from the ground? In that case, our coordinate axes will be here at the center of the plume. So, our x, this x will be 0 here and it will be pointing in the direction of the wind. The y will be 0 here at height h right above the chimney. Y will be 0 here and then y is pointing here and the z will start from here. So, what we will notice is that now our coordinate axis has moved h height up. In this situation for integration, instead of integrating instead of the limit of integration for dz being 0 to infinity, we will have the limit of integration being from minus h to infinity. And the reason why we will have it minus h from infinity is because we are starting integration from ground level all the way to plus infinity. So, this is very similar to the integration we did when we were assuming there is no chimney. We were still integrating from ground to infinity, it is just that our notation changed. And when you do it this way, then the result, when you integrate with this range, the result that you get looks like this. C is equal to this wind velocity here. So, this so far looks very similar to exactly similar to what we see when there is no chimney. The difference happens in the z. So, in z we get now z minus h whole square sigma z square. There is another easy way. So, if you there is another easy way to look at it, which is we still use the same old equation that we were where we were assuming that our coordinate axis is sitting at the ground level, but we shift the coordinate axis up. So, then what we transform is that the new z is equal to z minus h, new z is equal to z minus h, and then just the direct substitution there will also give us the same result. So, this is the first situation where one of our assumption is not met. Let us look at another situation. Now, when we are talking about Gaussian plume, when we are talking about a plume coming from a point source like a chimney, we assume that the smoke is free to move, there is no obstruction. But what if there is an obstruction? So, let us look at a scenario where the smoke is coming, but it is being obstructed. It could be a hill, a tree, a building, a wall. So, we have a chimney here and it is releasing smoke. We know the effective height and now there is an obstruction. So, let us say the obstruction is here. So, this is the distance of the obstruction, we will need this distance. And then the smoke hits the obstruction and it is not able to move forward. So, what will happen? Now, this is a case of the gaseous or suspended pollutant going through collision with a surface. Now, this collision could be elastic collision or inelastic collision. So, let us assume that this is elastic collision. So, what will happen is we will see that the smoke will be reflected back. So, now what is going to happen is the smoke is being reflected back, which means assuming perfect reflection, again here it may not be the case. So, you may have to account how the reflection is happening. Now, how will you find the concentration? So, let us say I give you a position here for a given x, y and z. find out the concentration, the obstruction is these many meters away from the chimney. How are you going to do it? So pause this video for a couple of minutes and try to think how you are going to solve, because you don't have to integrate and find something new. You just have to use your common sense. The answer is already there on the slide. So pause this video for a couple of minutes and think about it. Students, I hope that you were able to think, but even if that was not the case, don't worry. Notice one thing. If this is the perfect reflection, then the surface is acting like a mirror, the obstructing surface. So remember the mirror that we studied in our 10+2 physics? It's acting like a mirror, so you can trace back. So you can trace back the plume, and what you will see is that there is a virtual chimney here. There's a virtual chimney here with same center line, same height, same emission rate. It's not a real chimney, it's a virtual chimney. So now our calculations become very easy. So let's say this is capital X. We want to find concentration here at a small x, y, z. Then the virtual chimney is also capital X distance away from the obstruction. So the concentration here, the concentration of the smoke here or the pollutant here at x, y, z will be a summation. The concentration at x, y, z will be a summation of the concentration due to direct from source, which is a chimney, plus concentration due to reflected smoke. Concentration due to the original chimney, and then this is the reflected smoke that is coming from the, that appears to come from the virtual chimney. So we are going to add both the concentration coming from the virtual chimney and the concentration coming from the direct dispersion from the source. So how will this look like in your equation? So in your equation, which is given by C is equal to Q by 2 pi u sigma y sigma z e to the power minus half So this is for the direct plume, the plume that is not reflected, the yellow one. Now we'll have to add the emission coming from the virtual source, the virtual chimney. So this is the real chimney, and now from the virtual chimney. Now notice that the virtual chimney is also at the same height, has the same emission source, right? So it has the same y, same z as it does for the real chimney. Same, the wind velocity also will assume the same, because the virtual wind is blowing in this direction with the same. Now again we are assuming elastic collision. There is no energy loss. There actually will be energy loss. So the reflected plume will move at a different velocity than the actual plume, the real plume. But if we assume that this was perfectly elastic, no energy lost collision, in that case we can say u is also the same. What changes? What changes is the value of x. So remember, when you're finding sigma y, sigma z, x is integral to it. So for the reflected plume, you'll have to come up with new sigma y, sigma z values, which account for the x of this point from the virtual source. So remember, the small x, remember your coordinates are here, right? Z is starting from here, y is starting from here, x is starting from here, right? So remember, your x tells you the distance from the real chimney to the point where you want to find your concentration. So basically this distance is x. Capital X is the distance between the obstruction and the chimney. Now pause the video, take a moment to figure out what will be the distance of this point which is located at x, y, z from the virtual source, the virtual chimney, what this will be. Okay, students, I hope you figured out what this would be. It's very simple. Remember, this distance is x, this distance is x. So the distance between the two chimneys is 2x. Small x is the distance between the chimney and the point. So the distance between the point where you want to find the concentration in x direction from the virtual source will be given by 2x minus small x. So when you find out your sigma y, sigma z for the virtual source, you have to use a different value of x. That is the important part. So here you will have a different value of x. That is important. All right, let's look at another scenario. Now in this scenario, we still have the chimney. And this is the center line. This is the height capital H. Okay, so eventually your smoke will come and it will hit the earth. The plume will hit the earth. Remember, the dispersion is happening in all direction. Now what will happen? I mentioned that in this model, we are assuming that earth is impermeable. So if we stick with the assumption that earth is impermeable, what's happening to the smoke, the plume that has hit the earth? What I hope from the previous example, you have already figured out what is going to happen. This is going to get reflected back. And again, we can assume that this is going to be elastic collision, no energy loss, the reflection is going to be perfect. So let us paint it to clarify the difference between direct plume and the reflected plume. Now in this case, notice, in this case what is happening is that the earth is acting like a mirror, giving you perfect reflections of the smoke. In real life, the collision will not be perfectly elastic, except for gaseous pollutants. If you have suspended particles, they will most likely undergo an elastic collision. So there will be loss in momentum. They might even settle down depending upon their size and how the collision is, how much momentum they lose. So if you want to make this a more accurate model, you can account for all those. I'm just telling you what happens when we are dealing with gaseous pollutants who undergo elastic collision. So this is your direct plume. That's a large area to fill. And now let us paint your reflected plume. So this is reflected plume. So now if I want to find the concentration, at a point here for a given x, y, and z, I need to account for concentration coming from both the original plume and the reflected plume. Now once again, think about how you are going to model the reflected plume. So pause this video for a couple of seconds, think about it, and then return back. Alright students, I hope you figured out how to go about this. If you didn't, don't worry, no pressure. The virtual plume, we are going to again have a virtual plume. So earth is acting like a mirror, right? Earlier the obstruction was acting like a mirror, so there was a virtual chimney on the other side of the obstruction. Now here the earth is acting like a mirror, so we are going to have a virtual chimney on the other side of the mirror, which is the earth in this case. So apologize for my not so perfect drawing. My virtual mirror is not going to be an exact copy of the original mirror, obviously. So this is the virtual smoke. And now what we are going to do is we are going to add, to find a concentration at XYZ location, which is a point between where the reflected plume and the direct plume intersect, they meet. When we find a concentration of contaminant at XYZ, we need to account for both of them. So let's do it. Alrighty, so remember the formula of our concentration is given by, I'll just write on top of the plumes, C is equal to Q by 2 pi U sigma y sigma z e to the power minus half y square plus okay, this is what we have from the direct plume. Now what do we have from the indirect plume? Now okay, hold on, there is a difference. In the direct plume we will have z minus h square because it has a height. So we will have z minus h square, right? Now what about the indirect plume? So for indirect plume, the x, the horizontal distance, the x is going to be the same, the y is going to be the same, z is going to be different, because now this is different. This point is at a different height with the virtual plume. So here we are, this is the z height, z minus h is the distance from center line for this plume. So we have z minus h here. So this is the direct plume. Now C, due to reflected plume or the virtual chimney, virtual stack will be given by Q 2 pi u sigma y sigma z e to the power minus half, the y remains the same, so sigma y x remains the same, so sigma y sigma z will remain the same. The z is changing, let us look at it. Where is the center line of this? Center line of this plume is here. So this point is at this distance from the center line of the virtual plume. Now remember, this height is capital H, this height is also capital H because earth is acting like a perfect mirror. This height is Z. Now I am asking you to find out this height. How are you going to do it? So pause this video for a second and then try to figure it out and then return back to the video. Alright students, I hope this was not a very challenging question for you. Now this height, this question mark height is simply small z, which is the height of this point from the ground, plus the height of the virtual plume, which is capital H. So here we will have z plus h whole square divided by sigma z square, and we need to now add these two. So let us do that. I will clear up the plume color so that we have more space to write, but I hope you still realize that we are talking about summation of the reflected plume and direct plume. So now the summation, okay, I need to clear much things up. So let us remove the diagram. The virtual plume I have removed, but the reflection is still there for you to notice. So now we have C is equal to, we need to add these two terms, Q by, notice that Q by 2 pi u sigma y sigma z e to the power minus half y square sigma y square is same for both, is exactly the same for both. And since this part half minus half y square by sigma y square plus z minus h square by sigma z square sigma z square is an exponent, we can split them apart. So we can take this part common, and now we can put our differences in the bracket, which is e to the power minus half z minus h whole square by sigma z square plus alrighty. So this is our equation when we have reflection from the earth. Now let us look at a general situation. In a general situation, you have reflection coming from trees, so you will have partial reflection coming from hills, so you will have a reflection at an angle. Let me draw that, this will be fun. So this is the earth's surface, and this is your plume, and let us say here we have a hill, right? So we are at an angle to the horizontal. Now let us say the hill is acting like a perfect mirror, so your mirror is at an angle. So this is your homework, I am not going to show you how to do it, but it is going to be very easy, not very difficult. So this is your center line, so we are going to see a reflection, and the reflection So remember, if your hill is acting like a perfect mirror, so you need a 90-degree here, so the reflection, the new center line will be here, and then your smoke looks like this, and you're going to have a chimney here. If I draw the virtual chimney. So now, now you are at an angle. So all you need to do is, let's say you want to find out the, so this is reflection happening. You need to find out concentration at a given x, y, z. You need to add the concentration due to direct plume coming from the direct source, the original source, and the concentration due to the reflected plume, which is coming from the virtual source. Now here the difference is that the virtual source is at an angle because the mirror is at an angle. So you need to first figure out where the center line of your virtual source is. Now this height is h. You need to use some basic principles of trigonometry, and now you need to figure out where is this point in respect to center line in respect to your virtual source. So this is a homework, and maybe in one of the assignments we will take an extra discussion. We'll have a discussion with the students and talk about how to solve this, but I hope you can figure it out. It's basically adding up the concentration due to real source and the virtual source. Now these are simple examples, right? You have a tree, so there's partial reflection, the whole plume is not being reflected. You have trees, so you have diffused reflection. You may have inelastic collisions, you may have incomplete reflection. So you have a porous structure like a building, so it has windows, part of plumes goes in the windows, part of the plume is reflected. You might have multiple reflectors. For example, let's say there is a industrial estate, and then near the industrial estate you have high-rise buildings which are reflecting the plume. And if you go to our big cities like Noida and other industrial cities, you will notice that the skyscrapers often are close to each other, and if there is a chimney emitting a pollutant, then all these buildings will act like a reflector, like an obstruction. So this is where the smoke might get trapped between the buildings. So in this case, your reflection becomes a little bit more difficult. So you'll have to really think about the direction of the wind and how the reflection is happening. And basically your buildings will act like a mirror, either perfect mirror or permeable imperfect mirror, however they do. So these are the different iterations we can do on the model without modifying it. Now let's look at other scenarios where the derivation itself of the model will look different, and we may not end up with the model that we have, the Gaussian Plume model. So in this case, we are still saying that all the conditions for a model to be a Gaussian Plume model are true, are valid. So we are still using our Gaussian Plume model as a underlying model. Let's look at the scenarios where the assumptions we made in the derivation of the Gaussian Plume model are no longer relevant. So let's look at the scenario where there is no wind. Now in our equation for Gaussian Plume model, as I showed in the previous lecture, at the end of the previous lecture, if u becomes 0, c becomes infinity, which makes no sense. So what happens when there is no wind? When there is no wind, we have to go back to the derivation. So if you remember, in the derivation we had two things. We had dispersion and we have bulk action. So and then we added them together and we got the RHS of our equation. So it looked something like this. Sorry, this is y. Okay, and then we made series of assumptions like the diffusion is only important in yz because the bulk action is more relevant in x direction. We said there is no wind in v is 0, w is 0. We made all these assumptions. Now at this stage, we can make the changes we need to make in our system. So first is no wind. When it's a perfectly still situation, there is no wind. Let's say let's say we are in a room with still there is no wind, it's temperature controlled or not, but there is absolutely no wind, it's very still, that's an industrial unit. And we know that a particular contaminant, whether it is because of indoor air pollution I mean simple contaminants like VOCs, or because it's an industrial unit, so where a particular contaminant is being emitted in the room and we want to find out how it will spread through the room. In that case, because there is no wind, U, V and W will all become 0 and the diffusion will be important in all directions. So, we will end up with a very simple equation. This equation, and then we will proceed from here. So, we integrate this, we get our integral, and then we apply the boundary conditions, we get the integration constant and we get our model. Let us look at another scenario. One of the assumptions that we made was that the contaminant is not undergoing degradation. Let us say the contaminant is undergoing first order decay. So, first order decay means that the mass dm by dt of the contaminant will be equal to minus k, so first order decay constant m. So, this is what we know. So, we now know that there is another reason why the mass will be reduced. So, what we need to do? So, this is the second situation, contaminant is degrading. Now, here I am assuming first order decay, but it does not have to be first order, it can be 0th order, second order or something else dependent upon other concentration of other compounds, molecules, light, whatever. So, now in case of first order decay, dm by dt is equal to minus km, and km can be minus kc, and kcv, sorry, and v here is the volume of the parallelopiped, remember. So, we have del x, del y and del z. So, we can rewrite this as minus kc, del y, del x, del z, and when we put this, remember this equation originally had del y, del x, del z on both LHS and RHS, which we cancelled, and we this is del x, and we cancelled. So, we need to add this term in this equation. So, what we will end up with is something that looks like so, minus kc. So, we have first order decay. So, remember we are still conserving mass, dm by dt is equal to mass in minus mass out plus generated minus decay. Now, another situation, let us say we have other sources of contaminant. Let us say we have a particular contaminant that is being released in the industrial chimney, and let us say we are looking at some kind of organic compound, but the same organic compound is also released from other sources, let us say earth or agriculture lands. Now, we have generation happening. So, in that case we need to add a generation term within our parallelopiped. So, the generation can be per unit area. So, in that case, since our parallelopiped area is the del x, del y, so we need to account for that. The emission is coming in from here, the rate at which it is coming in. So, let us say the per unit area, it is a unit of mass is coming in. So, the bottom of this parallelopiped will be getting a del y del z per unit time, and then we need to also find out m out. So, we are going to use Taylor's expansion like we did earlier, and then we will get a term. So, in that case we will have to include a generation term here. Now, it might be different depending upon what are the other sources. Now, if we have simple multiple chimneys that are emitting, we can sum up their plumes. So, we can use computational abilities here. We can say, all right, one chimney, the plume looks like this, second chimney at this location is also releasing at this emission rate, so its plume looks like this, and then we can allow the plumes to overlap and we can add up. This is different, this generation is different. This is not coming from a point source, another chimney which is undergoing Gaussian plume too, so we do not add it, we have to include it here. So, it could be per area, or it could be some other sources that are releasing the gas. Okay, these are some of the basic differences that we see typically in our practical use of Gaussian Plume model, where sometimes there is no wind, sometimes wind is so high, let us say during a hurricane, but wind is moving in all directions, so we can't ignore them. So, or sometimes the contaminant is degrading, or contaminant. There are other generators of the contaminant which are not point source chimney type of generators. So these are some of the basic changes that we typically need to make when we are using this model. For example, in case of groundwater, it is very important to account for retardation. So then retardation factor will come on the LHS, and then there will be retardation that may come on the RHS too. Let's say we have a contaminant in the groundwater that is decaying first order. So in groundwater, for example, let's say we have a non-aqueous phase liquid, let's say oil, some kind of petroleum product that has seeped into the aquifer now, or has been injected into the aquifer, and now it is degrading with first order degradation constant. So we need to account for minus Kc. Of course, then we apply boundary when we integrate. After we are done with integration, to find the integration constant, we apply the boundary condition which are unique to the system, to the matrix, to the situation that we are dealing with. Alright students, this is all for today's lecture. In the next lecture, we are going to continue a discussion on the air quality model, but we are going to figure out a way how to calculate at what distance from the chimney the concentration of the contaminant will be maximum. Thank you.